Hello everybody, my name is Bruce Brasser. I'm a freshman at the University of South Carolina, Beaufort, and today I'm going to show you a new algorithm or technology or whatever I came up with that I call EEFs, Evolved Evaluation Functions. So yeah, let's get into it. So basically what you do is you use genetic programming to evolve evaluation functions. And yeah, so I'm going to go through an example using neural networks and generating cost functions, but you can do this for genetic algorithm, fitness assignment functions, you can do it for machine learning stuff, you can do it for whatever. Yeah, so this is going to be a basic example. So we generate the initial population of cost functions, and then you train neural networks, and this is, I just did it randomly generating them. You can do a bunch of different other stuff, you can seed them or whatever. And then you train neural networks using those cost functions on whatever data set you want. And then the cost functions receive a fitness based on the neural network performance. And then you do your regular genetic operators on them. And then you repeat the process. And you keep doing this until you get a quote unquote optimal cost function. So here's a quick example. This is just if we had a population of only 3 cost functions, which is not a lot, but this is just an example. So let's say this one got randomly generated to y hat divided by y. And we trained a neural network with it, and it got 68% accuracy. And we do the same for these ones. These got different accuracies, obviously. So then you assign a fitness to these cost functions based on the accuracy here, and you can use a bunch of different metrics on this. I did accuracy on the validation set, but you can do it on the trained set. You don't even have to use accuracy, you can use a bunch of different other metrics. So yeah, what I did to assign the fitness is I basically just took off the % sign and said, okay, this cost function has 68 fitness, this one has 11, this one's 83, but there's obviously a bunch of different other ways to do it. So then once they have their fitness, you can do the regular genetic operators on them, and you could say like, okay, well, this one has more likelihood to receive the crossover operation or whatever you want it to do. And then you just repeat that process until you get quote unquote optimal cost functions. And that's just an example for the neural networks. You can do it for a bunch of other stuff. So far I've used this to generate cost functions that in certain applications are better than categorical cross entropy and squared error. So those cost functions were found after like 3 hours of training on a kind of bad computer. So it does the work that humans did very, very quickly. And yeah, I believe this can be used to beat a bunch of benchmarks in the field of not just of neural networks, but of genetic algorithms, machine learning stuff. I managed to get within 0.15% of the world record benchmark on the MNIST data set, just generating custom cost functions on a convolutional neural network that was consistently trained on this fitness assignment was based on how well the network performed on the MNIST data set, and you just keep repeating that over and over again until you get your cost functions. And I managed to get within 0.15% of it, and I just found out what genetic programming is like a month ago. So if you give this to someone who actually knows what they're doing, I'm sure they would be able to beat the record or come very, very close. And I only trained it on for maybe 16 hours or something, so on a computer with 1 GPU. So I'm sure I'm very confident that many benchmarks can be beaten with this. And yeah, there's another kind of interesting thing about this is, I'll just use the example of neural networks again. It will kind of cater the cost function to whatever application you're doing. So if you are doing an application on the MNIST data set, it will generate cost functions that are specifically optimized for the MNIST data set. So sometimes that's a desirable thing and sometimes it's not, but it's a pretty interesting thing to note. And you can also, if you want things that aren't just catered to the MNIST data set or whatever data set you're doing, you can train a neural network on the MNIST data set, and you can train one on like the SciFAR data sets or whatever data sets you want, and you can include that into your fitness assignment function for the cost functions. So it will be catered to a wider variety of tasks rather than just one. And yeah, there's a bunch of other stuff you can do with this, but yeah, I think that's just it for the quick example. This is just obviously an example of neural network. I could do this for genetic algorithms or machine learning stuff. And yeah, if you want to collaborate, all my info will be in the description. And anything, yes, I'll also be doing like a code run through of one of the implementations I did of this, and going through line by line and explaining what it's doing. So that will probably be a different video, but I think that's all I have for now. If you have any questions, email me, leave it in the comments, and that's it. Oh, hold on. The code will be on GitHub. Okay, that's it.